I am Dr. J.V. Kamble, Assistant Professor of Soil and Water Engineering, College of Agriculture, Bhimrangudi, presenting lecture number 9 on topics soil loss estimation by universal soil loss equation, the parameters of soil loss equation, uses of universal soil loss equation, and limitations of soil loss equation. We know the control of erosion is essential to maintain the productivity of soil and to improve or maintain downstream water quality. The reduction of soil erosion to tolerable limits necessitates the adoption of properly planned cropping practices and soil conservation measures. There are several methods exist for the measurement of soil loss from different land units. These includes the measurements from runoff plots of various sizes for each single land type, small unit source watersheds, and large watersheds of mixed land use. However, to estimate soil erosion, empirical and process-based models are used. Universal soil loss equation. It is an empirical model. It estimates average annual mass of soil loss per unit area as a function of most of the major factors affecting sheet and reel erosion. It is a meaningful and useful estimate of sediment yield and can be obtained by using USLE. It also gives estimate for the long-term average annual soil loss from the catchment area. Wishmarer and Smith has developed universal soil loss equation and which latter modified with the recent data from the runoff plots, rainfall simulators and other field experiments. This equation is most widely used tool for estimation of soil loss from agriculture watersheds for planning erosion control practices. It provides an estimate of long-term average annual soil loss from segments of arable land under various cropping conditions. This application of this estimate is to enable farmers and soil conservation advisors to select combination of land use, cropping practice and soil conservation practices, which will keep the soil loss downwards. This USLE equation provides an estimate of long-term average annual soil loss from segments of arable land under various cropping conditions. The application of this estimate to enable farmers and soil conservation advisors to select combination of land use, cropping practice and soil conservation practices. The equation USLE is presented here. A is equal to RKLSCP. We'll see what is mean by A. A is the soil loss per unit area in unit time, tons per hectare per year. R is rainfall erosivity factor, which is the number of rainfall erosion index units for particular location. K is soil erodibility factor, a number which reflects the susceptibility of a soil type to erosion. That is, it is the reciprocal of soil resistance to erosion treatment of cultivated bare fallow. Then L is the slope length factor. It is the ratio which compares the soil loss with that from the field of specified length of 22.6 meters. We are going to move towards next factor, that is the S. S is slope stiffness factor. Means what? It is a ratio which compares the soil loss with that from a field of specified slope of 9%. Then we'll move towards the next factor, that is a factor C. C, which is cover management factor, a ratio which compares the soil loss with that from a field under standard treatment of cultivated bare fallow. Then we'll move towards next factor, that is P factor. P is support practice factor. What is meant by this P? It is a ratio of soil loss with support practice like contouring, strip cropping or terracing to that with straight row farming up and down the slope. L, S, C and P are each dimensionless ratio which allow comparison of the site for which soil loss is being estimated with the standard condition of the database. We'll discuss different USLE parameters in detail. First we'll discuss rainfall erosivity factor, that is R. This rainfall erosivity factor, rainfall erosion index, which expresses the ability of rainfall to erode the soil particles from an unprotected field. It is numerical value. The long field experiments, it has been obtained that extent of soil loss from barren field is directly proportional to the product of two rainfall characteristics. One, that is the kinetic energy, and another 30-minute maximum intensity. One is kinetic energy and another is 30 minutes maximum rainfall intensity of the storm. Here that it can be given in the form of equation. Rainfall erosion index unit EI30 of storm is estimated as EI30 is equal to KE into I30. Here K is kinetic energy of storm in metric tons per hectare centimeter. I30 is equal to maximum 30 minutes rainfall intensity of the storm. Then we'll move towards next factor. Next factor is soil erodibility factor, that is K. This factor K in the USLE relates to the rate at which different soils erode under the condition of equal slope, rainfall, vegetative cover and soil management practices. Some soils may erode more easily than others due to inherent soil characteristics. The direct measurement of K on unit runoff plots reflects the combined effect of all variables that significantly ease with which a soil is eroded or particular slope other than 9% slope. Some of the soil properties which affect the soil loss to large extent are the soil permeability, infiltration rate, soil texture, size and stability of soil structure. Also organic content and soil depth. These are usually determined at special experimental runoff plots or by use of empirical erodibility equations which relate several soil properties to the factor K. Here the soil erodibility factor K is expressed as a tons of soil loss per hectare per unit rainfall erosivity index from field of 9% slope and 22-meter field length. It is also determined by considering the soil loss from continuous cultivated fallow land without influence of crop cover or management. We are using the formula for calculation of soil erodibility index, that is K is equal to A0 divided by into bracket S into summation of EI. Here the K is soil erodibility factor, A0 is observed soil loss and S is slope factor. Based on the runoff plot studies, the values of erodibility factor K have been determined for the use in USLE for the different soils in India. Then we will discuss topographic factor, that is the LS factor. In other words, LS factor, it is the ratio of soil loss from a field having a specific stiffness and length of slope, that is 9% slope and 22.13 meter length, to the soil loss from a continuous fallow land. Then we will discuss next term, that is slope length factor, and that is L. It is also a ratio of soil loss from the field slope length under consideration to that of from the 22.13 meter length plot under identical condition. Then we are having next terminology, that is a steepness of land slope factor. It is also a ratio of soil loss from field slope gradient to that from the 9% slope under the identical condition. Here how we will going to calculate the ELS? So we have to use again Wishemeyer and Smith formula, which is given in the year of 1962. So ELS is equal to square root of L divided by 100 into bracket 0.76 plus 0.53 S plus 0.076 s square bracket complete. Here L is field slope length, it is in feet, and S is percentage of land slope. Wishemeyer and Smith also given another formula that we are using in MKS system based on the observation from cropland on slope ranging from 3 to 18% and length from 10 to 100 meter. That equation which is given by the Wishemeyer and Smith, that is LS is equal to into bracket lambda divided by 22.13 into bracket complete raised to m in bracket next bracket square bracket 65.41 sine square theta plus 4.56 sine theta plus 0.065 bracket complete. Here lambda is field slope length in meters, m is exponent varying from zero point 0.2 to 0.5 and theta is angle of slope. Then we'll move towards next parameter, that is crop management factor C. C, it is defined as a ratio of soil loss from cropland under specific crop to the soil loss from a continuous fallow land provided that the soil type, slope and rainfall conditions are identical. Here the variation in rainfall distribution within the year also affect the crop management factor and which affect the soil loss. Here, by considering all these factors, the erosion control effectiveness of each crop and cropping practice is evaluated on the basis of 5 recommended crop stages and which is introduced by Wishemeyer in 1960. And that stages are, so it is there, period F is for rough fallow lands and it includes summer plowing or seedbed preparation. Then period 1, that is the seedbed, and it refers to period from seeding 1 month and thereafter. Period 2, it is establishment stage and it is there for the duration ranges from 1 to 2 months after seeding. Then period 3, which is a growing period of this stage. In this stage it ranges from period of 2 to period of crop harvesting. Then the next stage, that is the stage number 5, and it is for the period 4, residue or stubble. Here after getting the information from the 5 stages, C is computed as the ratio of soil loss from crop plot to the corresponding soil loss from continuous fallow line for each of the above 5 stages separately for particular crop, considering various combination of crop sequence and their productive levels. And finally we are taking weighted average of the all C's. Next parameter, that is a next practice factor, support practice factor, and it is denoted by P. P, it is a ratio of soil loss with the support practice to that of straight row farming up and down the slope. Here this conservation practice consists of mainly contouring, terracing and strip topping. Here the soil loss varies due to different practices followed. After discussion of all the parameters related to USLE, we are moving towards uses or applications of USLE. Here USLE particularly used to predict average annual soil loss from field with specific land use conditions. It is also used to guide the selection of cropping and management system and conservation practices for specific soils and slope. It also predicts the change in soil loss that would result from change in cropping or conservation practices on specific field. It also helps to estimate soil losses from land use areas other than agricultural lands. This USLE equation also provides the soil loss estimate for conservationists to use for determining conservation needs. Then after discussion of the various parameter of USLE and uses of USLE, we are moving to limitations of USLE or limitations of universal soil loss equation. So we will see one by one what are the limitations of universal soil loss equation is having. Usually, if you remember in introduction part or introductory part of USLE equation, so I said that the USLE is totally empirical equation. So because of that, mathematically it does not illustrate actual soil loss process or actual soil erosion process. This equation was developed mainly on the basis of average annual soil loss data. Hence, it is having very limited application for the estimation of average annual soil loss of the given area. It is also having one more limitation, that is only used for assessing the sheet and drill erosion, but it is not used or it cannot be used for the prediction of gully erosion. Here, gully erosion is not accounted by the equation, and we know that this gully erosion is cause a greater amount of soil erosion. Then we are moving towards the next limitations of this universal soil loss equation, that is non-computation of sediment deposition. Here this equation is only estimating the soil loss, but it is not estimating the soil deposition. If the drainage on any site is improperly controlled and gully erosion is in extensive form, then this equation underestimates the sediment storage requirement of the retention structure. We have seen the use of USLE, then the limitations of USLE. Now, if this equation is having some limitations for its uses, then different scientists, they thought why we should not go for the different equations, and that equations which can overcome the limitations which are there in the USLE. So scientists of their rigorous study for over a decade developed the new equation, and that is reported by Kenneth et al. In 1991. That equation is revised universal soil loss equation. In other words, we are saying it RUSLE. So what difference we have observed in this equation? Here, new rainfall runoff erosivity term R is based on more gauge stations. Here, revision and addition for the given area, including correction for high R factor, areas with flat slope to adjust splash erosion associated with raindrops falling on ponded water. Here, the development of seasonally variable soil erodibility term K. Here, new approach for calculating cover management term with subfactors representing prior land use, crop canopy, surface cover, surface roughness. Here also the new slope length factor and steepness factor they have used, and which is reflecting real to inter-real erosion ratio. Then also they have new conservation practice factor for rangelands, strip cropping rotations, contour factor values, and subsurface drainage. Then after uses of the USLE or USLE, the people or scientists, they have observed that equation which is developed earlier, it was not sufficient to give the exact soil loss from the land. So the scientists, they came with new solution and new equation. That equation is modified universal soil loss equation. In other words, it is called muscle, and which is modified USLE equation by Williams in 1975. And here in muscle equation, muscle, by replacing the rainfall energy factor R with another factor called, that is a runoff factor, and this equation is expressed y is equal to 11.8 into bracket q into qp bracket complete raised to 0.56 k into bracket L S bracket complete into Cp. So here Y is a sediment yield from an individual storm. It is in metric tons. Here Q is storm runoff volume in meter cube. Qp is the peak rate of runoff in meter cube per second, and this K, LS and Cp, these are having the same meaning what in USLE equation it was having. In this model, Q is considered to represent detachment process and Qp is the sediment transport. It is a sedimented model and does not need separate estimation of sediment delivery ratio and is applicable to individual storms. Also, it increases sediment yield prediction accuracy from modeling point of view. It is it has the advantages that daily and monthly and annual sediment yield of watershed can be modeled by combining appropriate hydrological models with muscle. Here we'll see the example of soil loss estimation. So, example, calculate the soil loss due to erosion using USLE if R factor is equal to 100, K factor is 0.40, ELS factor is equal to 1.91, C factor is equal to 0.36 and P factor is equal to 0.75. Here the equation A is equal to RKLSCP. So here 100 R factor, 0.40 is K factor, LS factor is 1.91 and C is 0.36, 0.75 is the P. After doing the multiplications of all factors RKLSCP, so we'll get the soil loss, that is a 20.63 tons per hectare per year, 9.28 tons per acre per year. For you, one assignment is there. The Lingeri watershed area subjected to soil erosion and the following information is available. Rainfall erosivity index, then soil erodibility index, then crop management factor, conservation practice factor, slope length factor. So here we have to estimate the annual loss. Thank you friends.